So teaching the mole can be a real challenge, particularly for a beginning teacher, or if you're a science teacher whose chemistry subject knowledge is a little bit of a challenge. So this video is about giving you some guidance and suggestions, a method that you may use to teach the mole, which I hope you might find useful. You need to start by looking at what your exam specification says about the mole. I've got an example here from the UK AQA GCSE specification, which lists the initial things that you need to know about the mole. The next thing I've got is the periodic table from the same exam specification. AQA is one of the exam specifications. Obviously there are plenty of others that you could look at. I would strongly recommend that you always use your exam specification periodic table so that your students get used to what that looks like. They should be familiar with everything that's on here at this point in their education, and hopefully I'm sure you will be as well. But before you start teaching the mole, you need to make sure that there are one or two things that your students have got sorted and are very comfortable with. The first one is using their periodic table and understanding from that what mass number and relative atomic mass is. So have a look at your periodic table, have a look at whichever one you're using to teach, and make sure that the numbers that are on the periodic table with each element are absolutely clear to your students. They should know mass number from the work that they've done on atomic structure. So they'll know that mass number for any particular element is the sum of the number of protons and the number of neutrons. But what they've got on their periodic table is not mass number, it's relative atomic mass. So they need to be clear about what that means. On the slide I've got the example of chlorine, which has a relative atomic mass of 35.5 on pretty much all periodic tables. The reason that it's not a whole number is because there are two naturally occurring isotopes of chlorine. It has an atomic number of 17, but the mass number of the two isotopes are 35 and 37. So there's also an example on the slide of how you can calculate the relative atomic mass, knowing that there's 25% chlorine 37 and 75% chlorine 35. And what your students need to be able to calculate is what mathematicians call the weighted mean. So the example is there on the slide. You multiply the mass number by the abundance, add them both up, divide by 100, and that will give you your relative atomic mass. If your specification says you need to be able to do that, then you need to make sure your students have a bit of practice. Copper's another good one to try. The next thing your students need to be able to do is to make sure that their understanding of the symbolic representation we use in chemistry is clear. So the next slide has got a number of examples of the way in which we write both formulae of elements and of compounds with the stoichiometric number in front of it and what that actually means. At this point in time they need to know about atoms and molecules and ions, and don't start talking about moles till they're clear what this all means. So have a look at a slide like this and make sure that your students understand. So in the first line you've got H, 3Ne, H2 and 4H2, and they need to know that H means one hydrogen atom, 3Ne means 3 neon atoms, H2 means one hydrogen molecule with 2 atoms in each molecule, and 4H2 is 4 hydrogen molecules with each with 2 hydrogen atoms in. You get where this is going. So we have a number of more examples of this, gradually getting more and more complicated. You can choose what ones you might use with your students, but if I could just make a couple of points. In the third line you have H2SO4. No state symbols here. H2SO4 without state symbols, or strictly speaking gas, is hydrogen sulfate and it's a molecule. It only becomes sulfuric acid when it's H2SO4 aqueous, and then we're talking about hydrogen ions and sulfate ions. And it's quite important that you are very clear about the terminology you use here. So for this one, I would say this is one hydrogen sulfate molecule containing 2 hydrogen atoms, 1 sulfur atom and 4 oxygen atoms. On the last line, you've got ammonium sulfate and aluminium sulfate, both of which are ionic compounds. What terminology are you going to use to explain what you mean by two Al2SO4 There isn't really an easy word for an ionic compound. You can't talk about two molecules, or you shouldn't talk about two molecules. Two formulas is probably the best thing that you can use. So two formulas of aluminium sulfate, each containing two aluminium ions, 3 sulfate ions, and you can split up the sulfate ions into 1 sulfur and 4 oxygen atoms if you want to go that far. And then the third thing that your students need to know is relative formula mass. And I expect you will already have spent some time doing that with them. But it's worth checking it at this point to make sure that they're absolutely clear. So the example I've given you here is aluminium oxide. And there's some information on the notes on the slide to make sure that you go from talking about aluminium oxide to your students being able to work out the correct formula. Aluminium is in group 3 of the periodic table, therefore it's got 3 electrons in the outer orbit. Therefore, when it forms ionic compounds, it loses 3 electrons to form the Al3+ ion. Oxygen's in group 6, 6 electrons in the outer orbit. It gains 2 to make O2-, and then to balance the charges you need 2 aluminiums for 3 oxygens. So the formula for aluminium oxide is Al2O3. To work out the relative formula mass, they need to take into account 2 aluminiums to 3 oxygens. So they look up aluminium on the periodic table. Its relative atomic mass is 27. Oxygen is 16, so you need 2 aluminiums, 3 oxygens, and you add them up to give a total of 102. So once you've got those 3 things sorted and your students have had some practice and you've revised that a little bit, we're going to get on to talking about the mole. There's been a lot written about teaching the mole and the difficulties that it encounters, and one of the fairly definitive pieces of work on this was by Vanessa Kind at Durham University. It's about misconceptions in chemistry generally, but there's a really useful piece on the mole. On the next slide, there's an example of a fairly well-known equation, the reaction of sodium with water, just as an example of all the different ways in which you might be doing mole calculations with your students. So we've got sodium, which is a solid, and you'll be using mass of sodium if you were doing a calculation on the sodium. You've got water, which is a liquid, so you might be looking at the volume of the liquid, although at GCSE level this isn't very often required. You've got aqueous sodium hydroxide as a product, so you could be looking at the concentration of the solution, or you could be looking at the volume of a solution, depending on what its concentration is. And then finally, you've got hydrogen as a product, which is a gas, and so you might be doing calculations on gas volumes. And in the newer GCSE specifications, quite often that is a requirement. So it's just really to give an overview of all the different possible aspects of mole calculations that you might come across. Interestingly, in May 2019, the International Union of Pure and Applied Chemistry, UPAC, decided that they were going to redefine some of the fundamental units that are used in all of science, and the mole was one of them. Up until that point, the mole had been defined in terms of the number of fundamental entities in 12 grams of carbon-12, which in itself has quite a lot of difficult concepts. What it's now been defined as, because they are able now to work out the number of particles in a mole, Avogadro's number, to a higher degree of resolution, they have now defined the mole in terms of Avogadro's number. And you've got the old and the new definition on the slide. The new definition, interestingly, is closer to the definition that pretty much all exam specifications use. That is, that it defines the mole in terms of Avogadro's number. And so I think that's quite helpful for students. The definition that they'll need to know for their exam will depend on the specification, so you need to check that out. So now we need to have a look at what relative atomic mass actually means and make sure that the students understand that. So if we start from the perspective that the relative atomic masses of all the elements are the masses of the elements relative to hydrogen having a mass of 1, I'm not going to suggest that you use relative to carbon-12 having an atomic mass of 12, because I think that's actually quite a difficult concept. And from the point of view of GCSE students, then the concept of hydrogen being 1 and everything else being a multiple of 1 from hydrogen, I think is a much easier way to look at it. So I'm going to use some sweets as an example, as we quite often do in science. All right, so what I've got here is some beakers containing Smarties, Menstruals and Toffees. And for the purposes of simplicity, I could weigh each of these, but let's just say, I'm sure you can persuade your students, that the Smarties on a relative scale have a mass of 1, Menstruals have a mass of 2, and Toffees have a mass of 4. You can see quite clearly that in these 3 beakers, where I have 10 Smarties, 10 Menstruals, 10 Toffees, the masses are going to be very different. If I've got 10 Smarties, let's for argument's sake say they weigh 10 grams, then obviously if I've got 10 Menstruals, they're going to weigh 20 grams, and if I've got 10 Toffees, they're going to weigh 40 grams. And this is the concept that you need to get across to the students, is in chemistry we need to work with numbers of particles because it's at the particulate level that the reactions are going on. We can't work straight in masses if we don't know what the relative masses are. We wouldn't know what the mass of Menstruals is that we would need to have the same number of Smarties. We wouldn't know what the mass of Toffees were to have the same number as we've got Menstruals, unless we know their relative masses. Right, so we're going to be looking at building bricks to take this a little bit further. So you'll see it's all been carefully colour-coded. And hopefully you'll see where this is going. Right. So the red brick represents hydrogen. And we talk about stubs on the end of the brick. You'll see why in a moment. Okay. So what I have here are 2 hydrogen atoms. And the number of stubs is representing what their relative atomic mass is. So my question then is, here I have, with my green bricks, how many stubs? So there are 3 bricks, each with 4 stubs. So you can work that out. That's 12 stubs. Here I have, with my pink ones, 4 bricks, each with 4 studs. So I've got 16 studs. So if this is hydrogen, what are these 2? And at this point you get your students to look at the periodic table and hopefully they'll go, right, well, if it's hydrogen that's 1, then what is it that's got a relative mass of 12, and that's going to be carbon, and a relative mass of 16, that's going to be oxygen. So you've represented with your bricks the 3 different elements that we're going to deal with. So the next thing you do is you take more than one of those. So if we take 3 of these, what's the mass going to be? Okay, relative mass going to be. So hopefully they'll be able to do 3 times 16, 64 I think. Again, you can use any numbers you like with this, and it will depend on how confident your students are in dealing with these sorts of numbers, and you can work up to as many bricks as you've got, basically. You could also go, okay, what's this then? Or, what's this? And you can then talk about what the relative molecular mass of carbon dioxide is and what the relative molecular mass of water is. So you can see how you could play with these even with only a very few of the bricks. But the difficulty, and the next step is one of the difficult steps to make, is how does that relate to actual masses in grams? That represents 1 hydrogen atom. Now what is the actual mass of that hydrogen atom? It's very, very, very small. 1 atom of hydrogen weighs about 0.15 times 10 to the minus 23 grams. We cannot deal in masses of particles when you're dealing with chemistry on the macroscopic scale in the lab. But we do need to know how many particles are reacting with how many other particles. So what we need is a different way of relating the number of particles to the mass. So now instead of saying this is 1 atom of hydrogen, let's say it's 1 gram of hydrogen. So obviously in there's a lot of atoms. If on this model this is 1 gram of hydrogen, remember this is my oxygen, this would represent how many grams of oxygen? The answer to that is 16 grams. If we go to carbon, this would be 12 grams. Now the important thing to remember is that if I took a gram of hydrogen or 16 grams of oxygen or 12 grams of carbon, then I've got the same number of particles. And the question then becomes, well, what number of particles is that? And that number's called the Avogadro number. And that's what we call a mole. 1 mole is the amount of a substance that contains 6 times 10 to the 23 particles, whatever those particles may be. And the beauty of it is, because we've taken the number of particles in 1 gram of hydrogen, is it's the same number of particles in the relative atomic mass in grams of any element. And you'll need to practice that a little bit to get that across. So 1 gram of hydrogen, 16 grams of oxygen, 12 grams of carbon. We can go back to what we were doing before. Carbon dioxide, we've now got 16 plus 12 plus 16, that's 44 grams for a carbon dioxide molecule. So a mole of carbon dioxide has a mass of 44 grams. We can go back to our water. We've got 2 hydrogens, that's 2 grams, plus an oxygen, 16. 1 mole of water molecules has a mass of 18 grams. And then we can move on to the real stuff. So here we've got moles of a variety of materials. So here's a mole of copper, which has a mass of 64 grams. And this is a mole of sulfur, which has a mass of 32 grams. This is a mole of sodium chloride. I can't remember what the masses are of these, but you can work these out. Sodium chloride, sugar, sucrose, C6H12O6. Iron 3 oxide, it's a good one to do, and then make it a bit more complicated, hydrated copper sulfate. So that's copper sulfate with 6 waters of hydration in it. Those would be quite nice. They're easy to get together. Your technician hopefully would be able to weigh those out for you, and you could get the students to do some calculations, and you could do some measuring of mass as well. So the next slide has a few key points on it which relate to what we've just been talking about. The mass of 1 mole, which is called the molar mass and has a symbol of capital M, lowercase r, of a substance in grams, is numerically equal to its relative formula mass. 1 mole of substance contains the same number of entities. We use the word entities in chemistry to represent atoms, molecules, ions, could be electrons. Maybe in your exam specification, but again use the terminology that's in the exam specification. And that number is what we call the Avogadro constant, 6.02 times 10 to the 23 particles per mole, or entities per mole. So how big is Avogadro's number? Well, there is loads of stuff out there that you can check on the internet. So here's just a few examples on this slide. If you took the population of the Earth as being 6 billion, it would take about 100 trillion Earth populations to sum up to Avogadro's number. So it gives you some idea of how enormous it is. The one I particularly like is if you had Avogadro's number of donuts and you spread them equally all over the entire Earth, then the donut layer would be 5 miles deep. But I'll leave you to choose whatever sorts of examples you might want to give to your students. Going back to what I was just saying about entities, be aware of the fact that the entities that we talk about could be hydrogen atoms, they could be H2 molecules, and be careful about making it clear to your students that if you're talking about a mole of hydrogen atoms as opposed to a mole of hydrogen molecules, In the molecules, you'll have twice as many atoms because they are H2 molecules, and therefore twice the mass. So a mole of hydrogen atoms has a mass of 1 gram, a mole of hydrogen molecules has a mass of 2 grams, and that can be conceptually quite difficult for students to get their heads around. So there's a few examples on the next few slides of some exercises that you can get your students to do. The first one is related to working out relative formula mass of compounds and then molar mass. And all they need to do there is work out the relative formula mass and then stick a G after it for grams to give you the molar mass. Then there's some examples where you're asking your students to work out the molar mass of a particular entity, so it could be atoms, it could be molecules, it could be ions, and how many of whatever entity there is in that particular amount of hydrogen atoms, whatever. The next exercise is suggesting that you link different numbers of moles to different masses. So if in your chemistry equation you've got 2 H2O, then obviously you've got 2 moles of water molecules. So the mass of 2 moles of water molecules is not going to be 18 grams, it's going to be 36 grams. And your students need to be able to work that out as well. From that exercise, your students can be encouraged to get to the crucial formula that they need to know, which is that the number of moles of any particular material is its total mass divided by its molar mass. And you need to give them quite a lot of practice at working that out. On the next slide, you've got some examples of all the different types of calculations that you might need to do with moles. Now, this video is really about trying to help your students to understand what the concept of the mole is about. But the one thing that I would say is how you actually help your students to do calculations when they have a properly balanced, correctly written formula equation and they need to do some calculations related to it. So when you're teaching the mole, there are a few things that you need to make sure you're really clear about. I think it's really important that your students have a conceptual understanding of what the mole is about, so that you don't start from a point of view of this is how you do the calculation and then later on you introduce what the mole is actually about. The other thing you need to be very clear about is the terminology you use. I hope I've been consistent with my terminology through the whole of this video. You need to consider what your students' strategies are and how you assist them to make those strategies. You may need to relate back to what they've already done in their maths lessons, and sometimes they need to be reminded that they have actually done these things in their maths lessons. They can rearrange equations. Please think about what you're going to use to teach with. Are you going to use bricks? Are you going to use sweets? Are you going to use the real thing or a combination of all of them? And good luck with whichever method you choose to use.